Hi, I'm Wenjie Zhang from the University of New South Wales. In the following, I will cover the fourth part of the tutorial, related works, future works, and conclusions. Regarding related works, the following two topics are closely related to cohesive subgraph search or HINs, namely conventional cohesive subgraph models on homogeneous networks and heterogeneous information network clustering. Cohesive subgraph models on homogeneous networks have been extensively studied and many models have been proposed. Particularly, K-core model is defined regarding the minimum degree constraint, K-truss model regarding the strength of ties between two vertices. K-clique requires every pair of vertices in the subgraph to be connected. K-edge connected component model focuses on connectivity, and the densest subgraph model considers the density of the subgraph. For cohesive subgraph models on HINs, currently most of the existing models are extended from the cohesive subgraph models on homogeneous networks, and there also exist a few models which are defined by bringing new insights in other perspectives. K-core is a maximal subgraph in which each vertex has at least k neighbors in the subgraph. It is widely used in different problem settings to identify cohesive subgraphs due to the following important properties. First, it is fast and easy to compute. By iteratively peeling vertices not satisfying the degree constraint, the K-core can be computed in linear time regarding the graph size, and thus scalable to large graphs. K-core is especially useful in modeling the engagement of users in social networks, as the degree precisely captures the number of friends in the subgraph. The degeneracy of a graph is the largest case such that the K-core subgraph is not empty. It provides a good indication of the cohesiveness of the graph. K-truss is a maximal subgraph in which each edge is contained in K-2 triangles. It has some important properties such as each K-truss is a subgraph of a K-core. The edge connectivity of each K-truss is at least K-1, and the diameter of a K-truss is bounded by regarding the number of edges and the number of K. These properties directly follow from the definition of K-truss. K-clique is a set of K vertices of G such that each pair of vertices is connected by an edge. The K-clique is a complete graph with K vertices. It must be a subgraph of the K-truss, and it is also the most cohesive model among all the cohesive models on homogeneous networks. A K-edge connected component is a subgraph of G such that after removing any K-2 edges, the subgraph still remains connected. A K-edge connected component must be a subgraph of the K-core, and each connected component of the K-truss must be a subgraph of a particular K-edge connected component. This directly follows from the definition of K-core, K-truss, and K-edge connected component. The densest subgraph retrieves the subgraph with the highest density, where density is defined as the number of edges divided by the number of vertices. So after introducing the models of cohesive subgraphs on homogeneous networks, the next direction of related work is HN clustering. HN clustering aims to cluster all the vertices of the network into some sets, such that each set of vertices is densely connected internally. Compared with cohesive subgraph models on HN clustering is different in problem setting, criteria of defining cohesive subgraphs, and the general approaches. In terms of problem setting, cohesive subgraph search aims to search subgraphs satisfying the user's query requests, while HN clustering focuses on partitioning the entire HIN into a set of dense subgraphs such that each subgraph is weakly linked to others. Regarding the criteria for defining cohesive subgraphs are based on query parameters given by users. HN clustering, on the other hand, uses the same global criteria to partition the HIN. The general approaches are also different. Cohesive subgraph search solutions often work in an online manner, while HN clustering often based on some learning algorithms which are usually time-consuming and unscalable to large HINs. Next, I will very briefly introduce several works on HN clustering. The classic unipartite modularity is extended for bipartite networks and is computed as the accumulative deviation from the random expectation. The stochastic block model is applied for partitioning the bipartite networks based on the bipartite adjacency matrix. Another work on HN clustering utilizes the star schema to detect clusters with arbitrary number of taps and build a ranking-based generative model for each cluster. A social influence-based cluster method builds a social graph and an activity graph. Then, the social influence-based similarity is computed based on the social graph and activity graph. In the following, we will discuss the future work for cohesive subgraph search on HINs. The first line of future work is on the new models. As introduced in the tutorial, several cohesive subgraph models on HINs have been proposed, but they are still insufficient to cover all related real applications, especially for general HINs that contain various types of vertices and edges. Generally, there are three directions for studying novel cohesive subgraph models in HINs. The first direction is to extend the classic cohesive subgraph models that were developed for homogeneous networks. A potential research direction is to formulate new cohesive subgraph models based on the HIN connectivity and density, as these have not been comprehensively studied yet. The key challenge of the formulation is how to develop sound definitions of connectivity and density in HINs so that they benefit certain real applications. The second direction is to invent novel cohesive subgraph models like K-context. The third direction is to generate a new cohesive subgraph model by combining two or more existing cohesive subgraph models. This combination method has been studied extensively for homogeneous networks. For instance, we can combine the K-call and K-trust model together so that the result cohesive subgraph can maintain the properties of the two models. So in summary, there are various ways of formulating new cohesive subgraph models, but the feature of these models should be able to capture both the intensive link relationships among vertices and the type information of HINs. Another key challenge of cohesive subgraph search over big HINs is how to improve the efficiency to tame the huge data size and high computational complexity. Although existing works have made plenty of efforts to alleviate the issues of efficiency and scalability, there is still much room for further improving the search algorithms. To develop efficient algorithms, there are several potential research directions, such as to develop parallel algorithms to improve the efficiency, to develop index techniques to pre-organize the result subgraphs, and to develop approximate algorithms with approximation guarantees. An interesting future direction is to develop AI-powered cohesive subgraph search techniques. There are currently some initial studies on cohesive subgraph search over homogeneous graphs. In a recent study, the GNN model is applied to detect communities in the homogeneous network. So this problem has not been studied over HIN yet. In the models for cohesive subgraph search, often a parameter needs to be specified. The main challenges here are the different models have different parameters, and it is difficult to specify the proper values for these parameters. The future directions along this perspective may include automatic parameter suggestion based on statistics such as degrees, densities, and centrality, and to define an objective function to guide the search process. There are several online platforms for keeping large network datasets, such as Snap and Law, which maintain a large number of network datasets to allow online users to download them easily. However, most of these networks are homogeneous networks, and only a few HN datasets are collected into these platforms. It would be very beneficial to build an online repository dedicated for HIN research to keep and maintain public datasets, source codes, papers, and prototype systems. As a conclusion, in this tutorial, first we make a classification of existing works according to the classic cohesiveness metrics such as call, trust, click, connectivity, and density. And then for each class, we review the representative models and solutions thoroughly. Second, we perform a thorough analysis and comparison of different cohesive subgraph models and their corresponding solutions on bipartite networks and other general HINs. Third, we offer a list of promising future research directions of cohesive subgraph search or HINs, which can provide researchers some good starting point to work in this area. As a summary, in the tutorial, we comprehensively reviewed the following works for bipartite networks and general HINs according to the models such as call, trust, click, connectivity, density, and other interesting models. Thank you for attending this tutorial, and we welcome questions from the audience.